Hi, I'm Mrs. S with Owltree Montessori. Today I want to show you the Montessori Decanomial bead bars. The bead bars are the numbers 1 through 10, and there are 55 of each bead bar. If you are looking for one Montessori material that you want to get started with in your homeschool or your classroom, I highly recommend the Montessori Decanomial bead bars because they are so versatile. There are so many lessons you can give with this material for preschool through 6th grade. Preschoolers through kindergartners use this material for linear counting lessons. And kindergarten through 3rd grade use this for memorizing addition, subtraction, and multiplication facts. And the 4th through 6th graders use this material for pre-algebra and algebra expressions. If you find this video helpful, please give it a like. It really does help others find this video. And consider subscribing for more Montessori lessons for your homeschool and your classroom. The first lesson with the bead bars in the Montessori linear counting strand is the Bead Stair. This helps children associate the number and the quantity for 1 through 10. For an older child, it would associate them with the color of the bead bar and the number it represents. Here are 2 ways that you could lay out the bead stair with your child or your student. The first way is this triangular shape here from 1 to 10. And this second way is more of a stair. They are lining up along the left side, and you can see very clearly the numbers are growing by 1 each time. The next lesson in the linear counting strand are the teen numbers. So you can see that each number is made by putting a 10 and a unit number together, beginning with 10 and 1 is 11, going all the way to 10 and 9 is 19. A preschool child will use this to learn linear counting, the linear counting numbers and the quantity that makes that number. An older child would use this to learn the addition facts of 10 plus a unit number, making a teen number. They would really focus on 10 plus 1 is 11, 10 plus 2 is 12, etc. The other thing that you can do with this material is work on that fact family using the teen numbers. If 10 plus 3 is 13, then 13 minus 3 is 10. And 13 minus 10 is 3. Really good practice for that addition fact memorization. The next linear counting lesson would be the tens lesson. Once we got to 19, we would know that adding 1 more would be another 10, and we have 20. And then we would continue using the colored beads, 21, 22, 23, and so on until you were at 29, and adding a 10th one would be 30. Continuing on to 99 and then 100. Another game we can play with the bead bars to support place value hierarchy is the Infinity Street game. This is our homemade version of Infinity Street. You can see that we made yellow rectangles using construction paper to represent each number family. We have the simple family, the thousands family, the millions family, the billions family, the trillions family, and because I'm out of room to the left, I'm coming down here for the quadrillions family, then the quintillions family. We stopped with the quintillions family, but you could continue on in the hierarchy if you would like. Each family has a mailbox with their name on it, which represents the comma that we would put in a written number. Within each family, we have the units strip, the tens strip, and the hundreds strip in every family. Your child can place bead bars in each of the families and then read the number that they've created. We have 624 quintillion, 291 quadrillion, 564 trillion, 137 billion, 928,837,526. The addition snake game helps children learn and practice addition facts. You will need the black and white placeholder beads in addition to the colorful beads. The goal of the snake game is to turn the colorful snake into a golden snake by exchanging for 10. We will count, and when we reach 10, we will exchange. We are going to verify at the end that we have the correct answer using our addition facts. We start at the left. We have 5, 6, 7, 8, 9, 10. Exchange for 10, and I see we have 4 beads on the 9 bead bar. We still need to count. We'll use this 4 bead placeholder to remind us to count those 4 beads. We put our colorful beads at the top, not back in the box. We're going to use these at the end to verify that we have the correct answer. 4, 5, 6, 7, 8, 9, 10. Exchange for 10. We still have 1 bead to count. Our colorful bead goes here and our placeholder goes back in the triangle. And we have 9. We cannot exchange for 10, so here is where we stop. Turn the bead bars vertically to verify. We will take our colorful beads and match them against our 10s. I have a 7. And I need 3 beads here to finish this 10. I don't have 3 beads up here, but I do have a 5. I can exchange for a 3 and a 2. 3 plus 2 is 5. Back in the box. And now I have this 3. 7 and 3 is 10. This 9 matches with this 10, and I need a 1. Oh, I can exchange this 2 for 2 1s. That's fair. And we have 1, so there's another 10, and then this bead is our placeholder, and we have 29. This addition game for memorization is similar to the snake game, but it gives multiple addends and then you ask the child to look for combinations of 10. So I know that 8 and 2 is 10. I'm going to exchange for 10. I know that 6 and 4 is 10. I'm going to exchange for 10. And then I have 25 is my sum. For older children, showing them the math with multiple addends and how to make 10s to allow them to more quickly add multiple addends is the final goal. Another fact memorization game for addition is doubles addition. You can have your child lay out all the doubles facts from 1 plus 1 to 10 plus 10 and lay out the sums over here. And the interesting thing they will see is that all the sums are counting by twos. They're doubles. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 are the sums. Finding sums less than 10 is another addition game that you can use the bead bars for. There are a couple of ways that you could play a game finding sums less than 10. The first way is to pick a sum. We're going to sum for 9. Let's find all the combinations that make 9. We have an addend. Our first addend is 1, is our first part, and the second part is 8. 1 plus 8 is 9. The first part is 2, and the second part is 7. That equals 9. And continue on until you've found all the combinations. What you will find is that after 4 plus 5, the addends switch places, and you still have the same addends, they're just in a different place, but they still equal 9. This is the commutative rule of addition, and it's true for multiplication as well. So with this lesson, laying it out like this, you can also show them that rule that we can switch the places of the addends and it will still equal the same amount. Another way to play this game is to show children a flashcard or a little ticket with a fact on it and getting out the two addends and finding what they equal. So 5 plus 3, we can see 5 and 3 is 8. 4 plus 2, we can see that 4 and 2 is 6. Finding sums of more than 10 is very similar to finding sums of less than 10. I've shown you two ways here that you could play this game. I have picked the number 14 to be the sum, and then here I have found all the combinations of making 14 using two addends. Over here, you can give your child an prepared equation slip and ask them to make the two addends and find the sum that will be more than 10. When adding multiple addends together, we can use the associative law. The associative law says that when adding 3 or more numbers, the way they are grouped does not change the sum. I can add 3 and 5 together and get 8, and 8 plus 7 equals 15. I can add 5 and 7 together, that's 12, plus 3 equals 15. We often use parentheses to group two addends together. When I put the parenthesis around the 3 and the 5, that tells me I need to add the 3 and the 5 together first and then add the 7. I could put the parenthesis around the 5 and 7 and then I would know to add these together first and then add the 3. Addition with addends that are larger than 10 can be set up like this. We have an equation strip of 16 plus 27 written horizontally, and here are the beads representing those addends. We always start with the units. So we have 6 plus 7, and that is 13. We have our units, and now we add together our tens. That's 30 plus our 1 exchange is 40. We have a final sum of 43. The subtraction snake game helps children practice their subtraction facts. This snake game requires the use of the black and white placeholder beads and the light and dark gray subtraction beads. The gray beads will represent the amount to be subtracted in this equation. The goal is to turn this colorful snake into a golden snake. However, whenever we come to a gray bead, we have to stop and subtract. We'll start at the left. We have 9, 10. We can exchange for 10, and I see we have 6 beads we still need to count. We will use our 6th placeholder bead to help us remember to count those 6 beads. Our colorful beads will go at the top to be used to verify the equation at the end. We have 6, 7, 8, 9. Oh, stop and take away 4. Since we have this placeholder bead with a colorful bead, let's just exchange it for this 9 placeholder bead. I'll put the 3 over here and the 6 back in our placeholder triangle. Now we can take away 4 and we have 5 left. 9 take away 4 is 5. We'll use our 5 placeholder bead, and the gray bead will also go at the top to be used to verify this equation at the end. Our snake is shrinking down. 5, 6, 7, 8, 9, 10. We exchange for 10, and we have 1 bead we still need to count. One, and we need to stop and subtract 7. We have 11, take away 7. 1, 2, 3, 4, 5, 6, 7 leaves us with 4. We'll use our 4 placeholder bead. Our 10 will just go back in the box, and our gray beads up here. And we shrink down a little more. 4, 5, 6, 7, 8, 9, 10. Exchange for 10, and we have 3 remaining beads to count. 3, oh, we have to take away 1. That leaves us with 2. And our gray bead goes at the top. To verify and make sure that all of our colorful beads have been accounted for in this equation, and our gray beads are accounted for, all the subtraction we did, we're going to separate them into 2 groups. We have our 10 and our 2 10s and our 2 placeholder bead, and we have all of our gray beads here. Now we are going to match up our colorful beads with all of these beads here on the rug. I see we have a 7 here, and we have a 7 colorful bead. That takes care of that one. We have a 4 bead here, a gray 4 bead, but we don't have a 4 here. We do have a 6. We could exchange this 6 for a 4 and a 2. That's the same as 6. And now we can match this yellow 4 with the gray 4 and this 2 with our black placeholder bead 2. All right, I have a 1 gray bead here. We could take this 3 and exchange it for 3 1s. And now we can match our gray placeholder with this one, and we have 9 and 1 is 10, and 9 and 1 is 10. So now all of our beads are accounted for. The multiplication snake game helps children learn and practice the multiplication facts. It is very similar to the addition snake game in that we are going to turn this colorful snake into a golden snake, but at the end we are going to use multiplication facts. You will also need the black and white placeholder beads. We start at the left. 4 and 5 is 9, and 1 more is 10. We make an exchange, and we have 3 beads we still need to count. There's our 3 placeholder to remind us to count that 3. We have 3 and 5 is 8, and 2 more is 10. Put our black placeholder bead away and our colorful beads at the top. We're going to use our colorful beads at the end to verify. And we have 4 and 2 is 6. We can't exchange for 10 there, so we can now check our equation. We'll turn these vertical. Here is where we're going to do our multiplication. Let's put together all of the multiples. We have 3 4s, we have 2 of the 5s, and we have 2 of the 2 bead bars. So we have 4 times 3 is 12, 5 times 2 is 10, and 2 times 2 is 4. Here's where your child will practice their multiplication facts with the beads you've given them. Now, just as in the addition snake game, we're going to match our colorful beads to the 10s and make sure that we have the right amount of beads. We haven't left any out, we haven't added any in. 5 and 5 is 10. Let's put these 2 5s here by this 10. And then we have 4 plus 4 is 8, plus 2 more is 10. And then we have our 6 beads that we could not exchange at the end for another 10. We have 26. The skip counting chains help children learn and practice multiplication facts. You can see I've laid out the 3 skip counting chain up to 10 times 3. You could go further if you would like. A very young child would use this to simply linear count from left to right. So they would count 1, 2, 3 and lay out the arrow, 4, 5, 6 and lay out the arrow, and on. An older child would really begin to focus on the skip counting numbers, which is learning the multiplication facts. This work teaches the concept of multiplication through that skip counting and through repeated addition. We can even put little plus signs between and show that we are adding 3 each time. Multiplication is repeated addition. These are really good for strategy as well. When a child doesn't know a product, they could use skip counting or repeated addition to help them solve for the product. For example, if I know that 3 times 5 is 15, but I don't remember 3 times 6, I can use that 3 times 5 fact and then count on 3 more to arrive at the product that I need. If you would like, you could make little tickets, little fact tickets, kind of like flashcards, to show each fact with the 2 factors and the product to begin to make a bridge toward abstraction for your child. Another great thing about the bead bar work and making these chains is that we can show children the square number. When we stack these 3, they make a perfect square. 3 times 3 is a perfect square. That's 9. 9 is a perfect square. Drawing children's attention to these square numbers helps them with memorizing their multiplication facts, and it also gets them ready for the squaring work they'll do later on. When a child has practiced a times table by skip counting and they're ready to quiz themselves, one of the first ways they can do that is by turning the arrow cards upside down. So they have to try to remember what the next skip counting number is, and they memorize the skip counting that way. 3, 6, 9, yes. So they can go through, and you can also quiz them as well if you would like. One other way that you can make a bridge to abstraction is by making little tickets without the products, just the 2 factors, and laying them out so they can see the fact equation that they're finding the product for. Another way they can quiz themselves is by picking up the arrows. So they are mixed up and they have to see the product and find where it belongs. So that would be 3 times 3 is 9, 12, oh that's 3 times 4, 30, that's 3 times 10. If you would like, you could also lay out these cards so that as they are finding the facts, they can again see the 2 factors that they're finding the product for. The bead bar layout shows the array for each fact in a times table. You can see I've laid out the 3 times table from 1 times 3 to 10 times 3. You can also see that I have used all 55 of the 3 bead bars. That is why this material is called the Decanomial bead bar box. It allows me to lay out up to times 10 for each of the times tables. Visualizing the math facts as an array helps children with the concept of multiplication as well as memorizing the fact. You can see with 5 times 3 that this is 5 groups with 3 in each group. 5 times 3 is 15, and we can count the beads in this array, which is very concrete. When children lay out this material, they can do a follow-up work using graph paper and writing the fact and drawing the array, which will make a bridge to abstraction for them. The other thing that we can see in this bead bar layout is the square numbers. We can see that 3 times 3, 3 squared is 9, and 9 is a square number. For each of the times tables the children lay out, they will see the square number. When a child has practiced laying out the times tables, they can quiz themselves to see if they know the fact for each layout. They can take those little tickets, those little fact tickets cards, and turn them upside down and see if they can find the product. So 1 times 3 is 3. 2 times 3 is 6. 3 times 3 is 9. And they can continue on. Very concrete because they can count the beads. If they're not confident of that fact, if they forget it, they can count them up and have the product of those 2 factors. We can also show the reverse factors for a layout. So 1 times 3 can also be shown as 3 times 1, which would look like this. I would have 1 bead 3 times. No matter which position the factor is in, it still equals a product of 3. This is the commutative rule of multiplication, which says you can reverse the factors and you still get the same product. This is 1 group with 3 in each group. This is 3 groups with 1 in each group. 2 times 3 can also be shown as 3 times 2, which means I have 3 groups with 2 in each group. And even though I've reversed the factors, I still have a product of 6. If we reverse the factors of 3 times 3, we still get 3 times 3, which is 9, and the layout looks exactly the same. 4 times 3 can also be shown as 3 times 4, which is 3 groups with 4 in each group. 4 times 3 is 4 groups with 3 in each group, and 3 times 4 is 3 groups with 4 in each group, and we still have a product of 12. Another way to use the bead bar layouts to show the array for each multiplication fact would be to do it on a smaller scale. Instead of laying out the entire times table, I could use these tickets, or I could use flashcards to do one at a time. I have 1 times 3. 2 times 3 is 6. 3 times 3 is 9. 4 times 3 is 12. And I would continue on to 10 times 3. You could have your child record this on a piece of paper, just the fact or the fact, and drawing each array on their paper as well. We can show the reverse factors for a product using the bead bars. This demonstrates the commutative rule of multiplication, which says that no matter which position the factor is in, it still equals the same product. Here we have 4 times 7, which means there are 7 in each group, and there are 4 groups of 7. Here we have 7 times 4, which means there are 4 beads in each group and 7 groups, and that equals a product of 28. Here we have 3 times 9 and 9 times 3, and no matter which array we lay them out in, we still get a product of 27. This is helpful in memorizing the math facts because when a child understands this rule, they only have to memorize one fact for 2 separate times tables. If they know 3 times 9, in the 3 times table, they know 9 times 3 in the 9 times table already. This is demonstrated on our multiplication chart when we see 4 times 7 is 28 and we see 7 times 4 is 28. Your child gets to mark off 2 spaces as if they've memorized 2 facts when they've really only memorized or had to memorize 1 fact. Finding all the factors for one product helps a child memorize the multiplication facts, as well as prepares them for future factoring work, specifically finding the greatest common factor of a numerator and denominator to reduce a fraction to the simplest form. Here I have chosen the product of 12. We want to find all the factors that when multiplied together will give us a product of 12. When we start with 1, we see that 12 groups of 1 give us the product of 12. 12 times 1 is 12. Then when we try the 2's, we see that 6 groups of 2 give us 12. 6 times 2 is 12. Moving on to the 3's, we see that 4 groups of 3, 4 times 3, also gives us 12, and the reverse, 3 groups of 4 give us 12. So 3 and 4 are factors of the product 12. Lastly, we see that 2 groups of 6 give us 12, which is the reverse of 6 times 2. Our factors that give us the product of 12 are 1, 12, 2 and 6, 3 and 4. Your child can record this, the abstract, on a piece of graphing paper, all of the factors that give us the product of 12. We can make the squares for all the numbers 1 through 10 using the bead bars. When we multiply a factor times itself, we get a square number. This work shows that we are multiplying each number times itself and that it makes a square. We can also use this work to introduce exponents. So next to each fact, I have the exponent. We have this larger number that is the base number, and the small 2 is the exponent. The exponent tells us how many times to multiply the base number times itself. This work is very good for helping children memorize the multiplication facts for each of the times tables 1 through 10 by focusing on the square numbers within each times table. It also prepares them for future work with exponents. This is my daughter's recording work from her 6th grade curriculum using Montessori, where she drew out each square on graphing paper. She also has the fact written and the square written by each of her drawn squares. So this one says 4 times 4 equals 16, or 4 squared is 16. And she did that for all the squares 1 through 10. To introduce children to square rooting, we can build off of the squaring lesson. In the squaring lesson, we showed the children that when you multiply a factor times itself, you get a square number. We also showed them how to write the exponent for a square number. When showing them how to find the square root of a square number, we can show them that For example, 4 squared is 16, and we can look along the bottom, and if I pull the first bead bar down, that's a 4. It's as if this is the root that the rest of the square has grown from. So the square root of 16 is 4. The square root of 25 is 5. The square root of 64 is 8. When recording this work, your child can use the same recording sheet they used for the squaring work, and this time add the square rooting information. For example, here is the work done from the squaring work, where my child drew the square, did the math, 3 times 3 is 9, showed the exponent, 3 squared, and then she added the square root of 9 equals 3. And all that information, this becomes a beautiful chart that my child can access to remember squaring and square rooting. We can lay out all the bead bars from the bead bar box to show the multiplication tables from 1 to 10. This is called the Decanomial layout, or the table of Pythagoras. This is the vertical representation you can see along the left side of the rug. I have laid out the 1 times table from 1 times 1 all the way to 10 times 1. I have 1 times 1, 2 times 1, 3 times 1. Moving to the left, I've laid out the 2 times table vertically with 2 times 1, 2 times 2, 2 times 3, and so on. I have continued toward the right all the way to 10 times 1 to 10 times 10. You could also lay this out horizontally. Instead of the ones along the vertical side, I could do the ones along the top with the 2's underneath and lay it out horizontally that way. You could have your child lay this out visually and concretely and leave it like that. Or you could have your child do a written follow-up work where they write the multiplication facts for each times table. Another option would be to give your child a multiplication chart like this that represents all the facts on one sheet of paper. This chart has the factors written across the top and the factors written down the side, and in the middle where they meet are the products for all the multiplication facts. The multiplication checkerboard uses the bead bars to do multi-digit multiplication equations. It is a 9 by 4 rectangle with 36 squares. Along the bottom is where we will put numbers, digit cards, to represent the multiplicand, the number that we want to multiply. We have the units, tens and hundreds, the units of thousands, tens of thousands, hundreds of thousands, units of millions, tens of millions, and hundreds of millions. We can create a 9-digit multiplicand into the 100 millions place. Along the right side, we will put the numeral digit cards for our multiplier. This is how many times we are going to take our bottom number. We have the units, tens, hundreds, and thousands place, so we can create a 4-digit multiplier in the thousands place. Each square is the intersection of a multiplicand and a multiplier, and the color is the place value hierarchy of the product. For example, if I am multiplying a digit in the 100 millions place by a multiplier in the thousands place, that is 100,000 times 1,000 will give me a product in the 100 millions place. Building out the math for the place value hierarchy is one activity your child can do with this material, and it really helps them have a deep understanding of place value. The value of a bead bar is determined by which square it is in. If I place this 5 bead bar in the units category, it is 5. But if I move it to the tens place value category, it's now 50. This 5 bead bar represents the digit 5 in the tens place. Now it's 500, 5,000, 50,000, 500,000, 5 million, 50 million, 500 million. What if I place it here? Well, we're in the 100s place, so we have hundreds, thousands, 10,000s, 100,000s, millions, 10 millions. This represents 50 million. Allowing your child to read the value of a bead bar on the checkerboard prepares them for multiplication with the checkerboard and gives them great practice with place value hierarchy into the larger place value categories. Another good practice before starting multiplication is just building and reading numbers into the larger place value categories. This is 549,732,035. And you can see there's a 0 in the hundreds place. To do a multi-digit multiplication equation using the checkerboard, we are going to lay the multiplicand along the bottom in white numeral cards. The multiplicand is the number that we are going to multiply. You can see each of the numerals on the cards match the place value color of its category. Along this side, we're going to lay the multiplier in gray numeral cards, and again, the color of the numeral matches its place value category. The multiplier tells us how many times to take the multiplicand. We're going to multiply 542 times 32. I have also written the equation on this graphing paper, and we are going to record our products as we go along. We will have 2 partial products and a final product. We start in the units, so we're going to turn the tens card over so we can focus on our units. This tells us to take the numeral 2 times. So we have 2 times 2. Next we take 4 2 times. And finally we take 5 2 times. 5 times 2. The rule of the checkerboard is that there cannot be more than one bead in each square. So we're going to do our multiplication now, and we see that 2 times 2 is 4. We will exchange for a product of 4. 4 times 2 is 8. There's 8. And 5 times 2 is 10. And that is an exchange into the thousands place and a 0 here in the hundreds. That's 10. Let's record our first partial product. We have 4 in the units, 8 in the tens, 0 in the hundreds, and 1 in the thousands. We have a first partial product of 1,084. Now let's do the tens. Let's turn over our units card and turn up our tens card. This is telling us to take the numeral 2 3 times. Twice and 3 times. When your child becomes more fluent with the multiplication facts, they may not need to lay out the multiples. They might just look at 2 times 3 and say, I know that's 6. So instead, I'm just going to put the product 6 in that square. Next, we have 4 3 times, and I know that's 12. I'm going to make 12. And now we have 5 times 3 is 15. So I'll make 15. Again, the rule is only one bead bar in each square. So I see that 5 and 1 is 6. We're going to exchange for a 6. Now we can record our second partial product. We've started in the tens. So in the units place on our paper, we're going to put a 0 and write our first digit in the tens place, which is 6. 2 hundreds, 6,000s, and 1 10,000. We have a second partial product of 16,260. The final step is to combine our first and second partial products. So we do this by sliding our second partial product down to the bottom with our first partial product. You can see that this is the tens place, this is the hundreds place, this is the thousands place, and this is the 10,000s place, running diagonally down the board. So when we slide down to the bottom to combine, we want to keep our numbers in their place value categories. We need only one bead bar in each square. I see that 8 and 6 is 14. Going to exchange for 14. 2 and 1 is 3. 6 and 1 is 7. We now have our final product. So let's record what we have. We have 4 units, 4 tens, 3 hundreds, 7,000s, and 1 10,000. Our final product is 17,344. We can find multiples and common multiples using the bead bars. This is especially important for children who need to find the lowest common multiple in order to find a least common denominator between two fractions when doing operations with those fractions. We lay out the skip counting chains just like we did in the earlier lessons when we were memorizing the multiplication facts. In this review lesson, we introduced the vocabulary base number for that first number and multiples for all the numbers that come after the base number. Here we have a base number of 4, and all the numbers that come after are the multiples of 4. This is the base number 12, and the numbers that come after, 24, 36, are all multiples of 12. This vocabulary and practice will prepare children for finding common multiples between 2 or more numbers. When finding common multiples using the bead bars, we can lay out the multiples of each times table vertically down the rug just like we did in the Decanomial or the table of Pythagoras layout. We have our base numbers at the top, 2 and 3, and the multiples of 2 vertically and the multiples of 3 vertically. We can compare the multiples and find out which multiples they have in common. Writing them out on a piece of paper and circling the multiples, we can easily find the lowest common multiple, which will help children find the least common denominator for fractions when operating on fractions. We can find the greatest common factor of 2 or more numbers using the bead bars. One of the skills that is used with finding the greatest common factor is to find the greatest common factor of a numerator and denominator to reduce a fraction to the simplest form. We're going to choose a number, a multiple, that is not prime and that is less than 25 for this first introduction. We're going to choose 18, and we want to find out how many groups of 2 can we use to make the multiple 18. We have 9 groups of 2. Our factors would be 2 and 9. 2 times 9 gives us a multiple of 18. Let's try 3. How many groups of 3 do we need to make a multiple of 18? 6. 6 groups of 3, or 3 times 6, makes the multiple 18. So the factors are 3 and 6. Let's try 4. 20. No, 4 doesn't work. Okay, what about 5? Okay, we know 4 times 5 is 20, and then 5 times 5 is going to be 25. 5 doesn't work either. So we are done. We have found the factors that make the multiple 18. Those factors are 2, 9, 3, and 6. Let's choose another number. Let's do 24. How many groups of 2 do we need to make a multiple 24? Your child might say, hey, I know that 2 times 12 is 24, so they'll know they're going to make 12 groups. We have 12 groups of 2. 2 times 12 gives us 24. Let's try 3. How many groups of 3 make 24? We have 8 groups of 3. 8 times 3 gives us 24. Let's try 4. 6 groups of 4 also gives us 24. The factors of 24 are 2, 12, 3, 8, 4, and 6. And now we need to find what their greatest common factor is. So let's see which factors they have in common and find the greatest one. 2 is common, but it's not the greatest. It's actually the least. We have 3, but it's not the greatest. I see 6. 18 and 24 has a common factor of 6, and it is the greatest common factor. We can put greatest common factor, or the GCF, of 18 and 24 is 6. We can use the bead bars to introduce algebraic expressions and at the same time help children memorize the multiplication facts. Here we want to multiply a monomial, which is an expression of one term, times a binomial, which is the expression of 2 terms. We have the terms 4 and 6 inside these parentheses with the addition symbol, and outside the parentheses we have this term 4 that we want to multiply by the sum of 4 plus 6. We can do this 2 ways. The first way is to use order of operations and simplify for what is inside the parentheses. So let's do this. 4 plus 6 is 10. And if your child needs to see that, you can show them 4 plus 6 with the bead bars. Let's move down our times 4. And this says to take 10 4 times. We're going to do 4 groups of 10. And that equals 40. Another way to solve this is to use the distributive property of multiplication. The distributive property says to multiply a number by a sum, the outside number is multiplied by each term inside the parentheses, and then the products are added together. So let's do that. Let's distribute this 4 to each of the terms inside the parentheses. That would look like 4 times 4 and 4 times 6. And then we're going to add those 2 products together. First, let's do 4 times 4. So this is saying take 4 4 times. Here we have 4 times 4. And now we have 6 taken 4 times. And there's 4 times 6. 4 times 4 is 16. And 4 times 6 is 24. So let's make the product 16 and 24. And we're going to add these together, starting with our units. 4 and 6 is 10. We'll exchange for 10. And now we add our 10s, and that equals 40. Once your child has practiced lots of monomials times a binomial, you can introduce them to the algebraic expression A times B plus C equals A times B plus A times C. We can use the bead bars to multiply a binomial times another binomial. We are going to use the distributive property to multiply these two binomials. The distributive property says to multiply a number by a sum, we must multiply each term in the first binomial by each term in the second binomial. This means that we're going to take our first term in the first binomial, which is 7, and multiply it times 4 and times 2. So we will do 7 times 4 and 7 times 2. Then we will take our second term in the first binomial, 3, and multiply it by each term in the second binomial. So we'll do 3 times 4 and then 3 times 2. We first get out the bead bars that we are going to use to multiply by our second binomial. First, we want to take 7 times 4. So we are going to take 7 and we're going to multiply it by 4. We're going to build our rectangle of 7 times 4 using the bead bars. Next, we want to do 7 times 2. So we will lay out the bead bars to show 7 times 2. That completes our first term in the first binomial. Now we're going to take our second term in the first binomial and multiply it by each term in the second binomial. The first we have is 3 times 4. So here we have 3 and we have our 4. So here we're going to put our 4 groups of 3. Next we will do 3 times 2. And here we have our 3 times 2. And that finishes out our rectangle. And you can see if I push it a little closer together that all together this makes a rectangle. It is split in 2 along the top. So we have a 7 and a 3 and we've split our rectangle into 2 parts here. Along this side we've split our rectangle into 2 parts with 4 and 2. This creates our binomial. And we have 4 figures here. We need to multiply and add together. Now that we've laid out visually what we have, let's do the multiplication. This is representing our 7 plus 3 times 4. We have our first 2 terms in the first binomial times the first term in the second binomial. 7 times 4 is 28. We can show that here, 7 times 4. And then we have our 3 times 4, which is 12. And that's 3 times 4. And remember, we have to add the products together. So we have 28 plus 12, and that gives us 40. So we have 40 along our first row here. Down along the bottom, we have our second term in our second binomial represented as 7 plus 3 times 2. 7 times 2, and that is 14. You can show 7 times 2. And then 2 times 3 is 6. And we have 3 times 2 there. Okay, and remembering we have to add together our products, we have 14 plus 6, that's 20. And now we need to add everything together, and that equals 60. 40 plus 20 is 60. When your child has done a lot of practice with multiplying 2 different binomials together, you can introduce them to the algebraic formula for multiplying a binomial times a binomial. We can find the square of a trinomial using the bead bars. We're going to use 10 10 bars to make a 100 square. We're going to separate our square into 3, 5, and 2. Along the top here, I'm going to use these strings to separate between the 3, the 5, and the 2. We have separated our 100 square into 3, 5, and 2 along the top. Now we need to do the same thing along this left side. We have created a trinomial separating our 100 square into 3, 5, and 2 along the top and the side. We have created 9 figures. We can see that there are 3 squares here, here, and along the bottom here. And then we have 1, 2, 3, 4, 5, 6 rectangles. Let's look at what we have, starting with our squares. We have a 3 times 3 square there. So we're going to label 3 times 3. And we are also going to build that with our bead bars. Here's our 3 squared. Now let's look at this big square in the middle. That's 5 times 5. We have our square, 5 times 5, and we've labeled our middle square 5 times 5. We have one more square down here at the bottom. That is 2 times 2. There we have built 2 times 2. Let's look along this top row and see what else we have here. Here we have 3 times 5. 3 times 5, right there in the middle. I can also see that we have 5 times 3 right along this side too. Here's a rectangle that is also 5 times 3. Let's build that. That would be 5 groups of 3 in each group. We have 5 times 3 and we have 5 times 3 rectangle here. Let's finish our top row. We have 3 times 2 here. So let's get out our 3 groups of 2. I can also see that we have 2 times 3 down here. 2 times 3 and 2 times 3. Let's see what else we have. We have something left here on this side. That is going to be 5 times 2. 5 times 2, built there, and we have it again here. We have rebuilt our square using our bead bars to show each product of the factors. In our first row, we have 3 times 3 is 9, 3 times 5 is 15, and 3 times 2 is 6. So we have 9 plus 15 plus 6, and that gives us a sum of 30. In our second row, we have 5 times 3 is 15, 5 times 5 is 25, 5 times 2 is 10, so that's 15 plus 25 plus 10, which gives us a sum of 50. And in our third row, we have 2 times 3 is 6, 2 times 5 is 10, 2 times 2 is 4, that's 6 plus 10 plus 4, and that gives us 20. And now we need to add all of it together. I know that 30 plus 20 is 50, and 50 plus 50 is 100. And that gets us to our 100 square. To solve this algebraic equation, we want to expand it. So now we're going to take a look at what we have here and expand it mathematically along the top. The first part is that we need to square each term. We need to say 3 squared, 5 squared, and 2 squared. And we did that here with our beads. We've expanded it here by writing 3 squared plus 5 squared plus 2 squared. The next thing we're going to do is take twice the product of the first and second term. The first and second term is 3 and 5. So the product of 3 times 5 times 2. We have our 3 times 5 and our 5 times 3. The next thing we need to do is take twice the product of the first and third terms. That would be 3 times 2. Here we did it 3 times 2 and 2 times 3. We have 3 times 2 times 2. The last thing we need to do is take twice the product of the second and third terms. That would be 5 and 2. 5 times 2. We have that here, and we have it here. We have it twice. We have plus 5 times 2 times 2. Now we have expanded our math from here, and now we need to simplify it. We can first simplify our squares. 3 squared is 9, 5 squared is 25, and 2 squared is 4. Next, we need to simplify what's inside our parentheses here, our multiplication of our first term and our second term. So 3 times 5 is 15. Then we have our multiplication for our first term times our third term. That's 3 times 2, and that's 6. And then we have our product for 5 times 2, which is our second and third term, and that is 10. But we still need to multiply each of these by 2. So we have 2 times 15 is 30. 2 times 6 is 12. And 2 times 10 is 20. And the last thing we need to do is add them all together. 9 plus 25 plus 4 plus 30 plus 12 plus 20 gives us 100. And we're back to our 100 square. Your child can record on graphing paper, drawing out the 100 square and showing our squares and rectangles with our factors and how we added it all up to 100, and then they can expand it down on the bottom. We can pass from one square to another square using the bead bars. This lesson gives children experience with the squares of binomials and with the multiplication facts of square numbers. We want to pass from a 7 square to an 8 square. What do we need to add to this 7 square to get us to this 8 square? Well, we know that 7 times 7, or 7 squared, is 49, and 8 times 8, or 8 squared, is 64. So we need to go from 49 to 64. What do we need to add to build in here to get to an 8 square? Well, we have 7 at the top, and I know if we add one more, that would be 8. So let's build a 7 on this side, and we need to keep our square shape, so we'll add a 7 down at the bottom. And now we have 8 across the top, and we have 8 down the side. But we need one bead here to have 8 down the right side and 8 along the bottom. So now we have an 8 square here. What did we add? We added 7 plus 7, or 7 times 2, that's 14. And then one more bead is 15. So we added 15 beads to get from 49 to 64. Let's break this down and look at our square and rows. So if we look at the top row with the square and our 7, we have 49 plus 7, and that gives us 56. In our second row, we have 7 plus 1, and that gives us 8. And 56 plus 8 is 64. We can show that 64 equals 49, there's our 49, 14, that's our 2 times 7, plus 1, that's our 1 bead here. Your child can record the math for this, and here is a simple math equation that they can show between just the visual and the algebraic formula. This shows that 8 squared equals 7 squared plus 2 times 7 plus 1 squared. When your child has practiced lots of passing from one square to the next consecutive square, you can prepare them for the algebraic formula by replacing numbers with letters. In algebra, we use letters for formulas. So in our equation, A is going to equal 7 and B will equal 1. So we have here A squared, and then we have A times B, B times A, and we have B squared. And the algebraic formula looks like this. So once they understand that we can replace numbers with letters, then you can show them this formula that you can use to plug any number into. C squared equals A plus B squared equals A squared plus A times B plus B times A plus B squared. Our equation, if we plug in our numbers, A equals 7 and B equals 1, we have, and of course C equals 8, we have 8 squared equals 7 plus 1 squared, 7 plus 1 is 8, 8 squared, equals 7 squared plus 7 times 1 plus 1 times 7 plus 1 squared. We can also pass from a square to a non-consecutive square. Here we want to go from a 5 square to a 9 square. Again, we look at the multiplication for each square. We have 5 times 5, so this is a square of 25, and we have 9 times 9, which is a square of 81. And now we need to figure out what we need to add to 25 to get us to 81. Looking across the top, I see that there are 5, and I know that 5 and 4 is 9. So there's a difference of 4 between 5 and 9. Let's take our 5 bars and we will build out from our 5 square 4 more, keeping our square shape. We have built out on either side of our 5 square 4 more groups of 5. And now what we have here in the middle is we're going to have a square of 4. I can see 4 more along here and 4 more here in a perfect square. We have built 9 across the top, 9 down the side, 9 across the bottom, and 9 up this other side. So we now have a square of 81, starting with a square of 25. Let's look at each row individually and see what we added. In our first row, we had 25 plus 20, which is 4 times 5, to give us a sum of 45. In our second row, we have 20, again, 5 times 4, or 4 times 5, plus a 4 square, which is 16, and that gave us 36. When we add 45 and 36 together, we get 81. So 81 is 25 plus 40 plus 16. We can show your child this math to represent what we've done here. We see it says 9 squared equals 5 squared plus 2 times 20, which is 20, 20, that gives us 40, plus 4 squared, which is 16. And you can have your child write it out like this. When your child has had lots of practice moving from one square to a non-consecutive square, you can prepare them for the algebraic equation by showing them that we can replace numbers with letters. In our equation, A is going to equal 5 and B is going to equal 4. We can show that this is A squared, this is A times B, B times A, and this is B squared. This is our algebraic formula. C squared equals A plus B squared, which in our case is 5 plus 4 squared, equals A squared plus A times B plus B times A plus B squared. When we plug in our numbers 5 and 4, here's what it looks like. C squared is 9 squared. 5 plus 4 squared is 9. 5 plus 4 squared, which is 81. And to expand this further, we have 5 squared plus 5 times 4 plus 4 times 5 plus 4 squared.